Hello everyone, I am Xingying Liu. I'm a third-year PhD student in the University of Manchester. This is my poster presentation to Infrared Millimeter Wave 2020. My submitted poster is terahertz spectroscopy on sputtering germanium thin films. The reason why we study germanium thin film is, as we all know, silicon, although it is the most commonly used semiconductor material, suffers from low efficiency due to their indirect bandgap. Then we started to look into other group 4 materials, in this case germanium and tin. Germanium, although by itself, is still indirect bandgap, but with putting tin into it to form an alloy, the bandgap will change into direct bandgap. Apart from this direct-indirect bandgap transition, material properties such as mobility, carrier lifetime, absorption coefficient will change with tin content as well. This is really good for making different devices. Now back to our sample. This sample set is germanium tin thin films grown on germanium substrate by sputtering. All films are around 350 nanometers. In literature, germanium tin alloy should have longer carrier lifetime and higher mobility with higher tin content. To extract those carrier lifetime and mobility out from samples, we employed terahertz spectroscopy to characterize our samples. As shown in this diagram, when we shine terahertz pulse into the sample, either reflected pulse or transmitted pulse will be collected by the detector, similar to every spectroscopic technique. This won't damage the sample. Furthermore, the energy of excited carrier is in the terahertz range. Therefore, terahertz spectroscopy is quite sensitive to conductivity. Additionally, with an optical pump, which excites the sample, the terahertz pulse can be recorded as a function of time after pump arrives. This allows us to study how photoexcited carrier recombine. Now let's look at our experimental setup. We performed terahertz spectroscopy on those germanium tin samples in reflection mode. As the 6 substrate give low transmission signal, a 1.5 micron optical pump was added to excite our samples. This allows us to study the carrier recombination mechanism. Let's go to the experimental result part. As we took pump decay from all 3 samples with different tin content. Each sample had 4 different pump fluids. This is just by adding different ND filter into the pump. The terahertz signal is proportional to photoexcited carrier concentration, so this decay shows how fast carrier recombine. We can see with higher tin content, this decay is generally sharper, suggests the carrier lifetime is shorter with high tin content. Now if we look at the extracted mobilities, we can see generally with higher fluence, which results in more carriers, the mobility will drop. This is due to the stronger carrier scattering, such as carrier scattering, carrier defect scattering, carrier phonon scattering. Also, there is a trend of lower tin content, higher mobility. With 1.5% germanium tin, the lifetime goes up to about 3.5 nanoseconds, which is quite long. However, if we reference to literature, the mobility and carrier lifetime should be both higher with higher tin concentration, which doesn't match with our experimental results. This could be due to the low crystalline structure and more defect states when we added tin. In conclusion, we measured 3 germanium tin thin film samples with different tin content. This experimental result shows with higher tin content, the mobility and carrier lifetime will drop. which is exactly the opposite with the prediction in literature. This suggests the material property of our samples are still dominated by defects introduced from growth mechanism. This result provides us direct feedback to improve growth of germanium tins in films.